computer science educators. As you prepare to facilitate this lesson with students, I want you to see this activity as more than just a fun coding task. What students are really building is a simple game engine. Inside this small project are 3 foundational computer science ideas: variables, loops, and logic, and even a bit of game theory. So let's start with variables. When students create the variable called hand, they're creating a storage container. The microbit does not understand words rock, paper, or scissors. It only understands data. So we map numbers to meanings. 1 equals rock, 2 equals paper, 3 equals scissors. That abstraction is important. Students may not immediately understand why we're using numbers instead of words. It helps to say explicitly, computers prefer numbers because they're easier to compare and process. A common issue here is naming. If students don't name the variable exactly hand, they can get confused when following the tutorial steps. Another common issue is that students forget to actually click make a variable, and then they don't see the new block appear. When that happens, instead of fixing it for them, ask, what steps create new blocks in the variables menu? That small pause will reinforce cause and effect. Next comes the event block on shake. This is where we introduce loops. Even though students won't see a forever loop, the shake event acts like repetition. Every time the device is shaken, the code inside runs again. This is an event-driven loop. It's important for teachers to recognize this because students often believe loops only count if they see a block labeled repeat or forever. Here, repetition happens through interaction. Inside that shake block, students set hand to a random number between 1 and 3. This is where game theory quietly enters the picture. Rock, paper, scissors only works if choices are unpredictable. If the microbit always chose rock, it wouldn't be a fair game. Randomness creates fairness and uncertainty. If students accidentally choose 0 to 2 or 1 to 6, their logic later won't match. And when that happens, ask them, what numbers does your logic expect? Help them to trace the system rather than patching the symptom. Then we move into logic, the if, else structure. This is the decision-making engine. The microbit checks if hand equals 1, show the rock. Otherwise, check if it equals 2. Otherwise, it must be 3. This is conditional logic, the computer evaluating statements and branching based on truth. Students commonly confuse checking a value with changing a value. They may use set hand to 1 instead of hand equals 1. When that happens, ask them, are you asking a question or are you changing the answer? That distinction is huge in programming. Another common issue is misplacing blocks. If a show icon block sits outside the conditional structure, every shake may display the same result. Instead of correcting it immediately, ask, how does the microbit know when to show that icon? That question helps them reconnect the logic to the output. When students test their program, this is where your role shifts from instructor to coach. Resist the urge to fix broken code. Instead, ask, what do you expect to happen? What is the value of the hand right now? Which condition should be true? Debugging is where real learning happens. If your students decide to try the extension activity and add a score counter, they'll need to recreate the tutorial code in the new project space. This will give them access to other necessary inputs. Once students have their rock, paper, scissors game working in the new space, they're now ready to turn it into a real game by adding scorekeeping. First, we need to create a new variable called score. So we go to variables, make a variable, and we're going to write score. Just like hand, this variable will serve as a container that stores information, in this case, how many points the player has. Next, we add an event block. So we go to Input, and we are going to choose on button A pressed. and drag it into our workspace. Inside that block, we use change score by 1, and we can find this inside the variable container. This tells the microbit to increase the score every time button A is pressed. But if we want students to see the update, we add a show number score block underneath. To do this, we go to Basic, Show Number, and then make sure to update that 0 to Score. Then we add another event on button B pressed. So we go to Input, and we are going to select on button A pressed, but we're going to use that drop-down menu to change that to B. Inside that one, we will use Set Score to 0. So again, go Variables, Set Score to 0. Again, I want my students to be able to see that the number has been reset. So I am going to click Show Number, nestle it in that variable, and keep it at 0. This will make it so that the score resets anytime button B is pressed. If you choose to add scorekeeping, you introduce state management. Creating a score variable teaches students that computers can remember information over time. Using change score by 1 on button A shows incremental updates. Using set score to 0 on button B demonstrates resetting the stored data. A frequent mistake here is using set score to 1 instead of change score by 1. When that happens, ask, are we replacing the score or are we adding to it? That question alone builds deeper understanding. By the end of this activity, students have unknowingly built the foundation of every digital game, a system that stores data, responds to input, makes decisions, repeats actions, and updates state. If you remember nothing else while facilitating, remember this: don't rescue too quickly. Ask guiding questions and let students trace their logic. The goal isn't just a working rock, paper, scissors game. The goal is helping them think like programmers.